can go till 7 and then make a brief break, like 15 minutes to catch up there, and then continue one more hour, or maybe 1 hour and a half, no longer than that. So, one thing we did last lecture was to introduce this thing called the first order formalism. And the main idea is that instead of concentrating in the metric, we turn our attention to this guy, the feedback. And if we know the feedback, we know the metric because of this relationship. So people think of the feedback as the square root of the metric because feedback squared gives the metric. And we define a one form like this. This is not just one form, it's a collection of one forms. Actually, it's a Lorentz vector of one forms. And we say it's a Lorentz vector because under a local Lorentz transformation, we have so this is the transformation law of a vector, and that's why we say this field line it's a Lorentz vector whose components are one forms. And we also saw that we need to introduce a connection omega, which is also a one form. So this is not a tensor, it's a connection, but it has two indices, two Lorentz indices, and it has a third hidden index. That's the form index. Okay. So it is a one form with two Lorentz indices. And I didn't say it last class, but this is antisymmetric. If you demand that the Lorentz covariant derivative of the Minkowski metric is 0, then this is equivalent to showing that this has to be antisymmetric. So people usually demand that. That's put in by hand. But we'll see it makes sense. And with this Lorentz connection, we built a covariant derivative. Such that this is what we call the torsion, and we also define this as the current. And these guys are two forms. You can see that because if you take the exterior derivative for one form, you get a two form. Same thing here, and here you have the product of two one forms. And these satisfy identities. And the nice thing about these identities is that they show that these characters, the field band, the spin connection, curvature, and torsion, form a complete set of variables to describe geometry. There are no more things, because if you keep taking derivatives, you just find the old guys yet again. So that's like the kinetic part of this story. And the dynamical part comes when you pick a Lagrangian. We don't actually need that we see. So the first thing is pretty obvious, because this is what we have. We have these characters, so we're going to use them. We also have these two elements. They come from free, when you have the Lorentz algebra. It has to be a 4 form, because we're in 4 dimensions, so we want to integrate this Lagrangian into the whole of space-time. And we're demanding that it be Lorentz invariant. The talk we just heard, it's about breaking Lorentz invariance. We're going to be conservative here. We're going to keep Lorentz invariance, but of course, it's a point to you have to have your eyes open, because it may not be true. Who knows? And actually, I'm going to show you in the end some possible Lagrangians which are almost invariant. Which, if you perform a Lorentz transformation, they do not remain invariant, but they change by a total derivative, which is almost invariant. People usually don't care if they add a total derivative, but it may not be so innocent. They have some consequences. And actually, you gave me a list of possible Lagrangians built with these indications. And the list wasn't very long, it was like 8 possibilities. And from this small list, we picked 3, which belonged clearly to a family. So the index 0, 1, 2 refers to the number of curvatures. Here there's no curvature, only field lines, there's 1 curvature, 2 curvatures. And we show that this is the Einstein-Hilbert Lagrangian. So that's a summary of the lecture from last Friday. And we're going to build up from here. So, if this is the Einstein-Hilbert Lagrangian, what are the other 2? First thing. Actually, it's much more easy to see what these are than this one, curiously. So let's take L0. And we're going to write the hidden index here in all of these field variables. So each field bind is a one form, so it gets a differential, and we have 4 differentials because this is a 4 form. And this is wedge product, the exterior product, so this is actually anti-symmetric in all of the indices. So this here is just that. And this part here is the epsilon A, B, C, D times 4 times a matrix with A, B, C, D. And what the epsilon does, it's taking the determinant of this matrix. So this part here is equal to the determinant times that's it. And so what we got here is this is 2 epsilons completely contracted among themselves. They have 4 indices. This is a number. This is 4 factorial. That's 24. It doesn't matter, it's a number. And this determinant, is, we showed it last lecture, is the square root of the metric. So this L0 is actually nothing else than the volume element. It's a constant times the volume element. And this is actually what people call the cosmological constant. Because if you have the usual Lagrangian is R, that's the Einstein-Hilbert Lagrangian, but people usually add a cosmological constant like this. So you see, the cosmological constant term is a constant times the volume element. So it is just what we have here. So the Laplace family is actually very conservative, you know? The L1, Einstein-Hilbert, L0 is the cosmological constant. So far we have learned quite nothing new. It's just a new way of writing old things. What is L2? So this R is a 2 form, so it has 2 hidden indices that go with the differentials. Another R, 4 differential. I'm going to go a bit faster here. And now these Latin indices I'm going to turn to Greek in this is using the field bind. So let us use alpha, beta, gamma, and delta. And so again, this is the determinant of the field bind. And when you have these two epsilons, they don't have the same indices, but they are multiplying. So you write them as a generalized Kronecker delta. So this is L2. It's quadratic in the curve. Two curves. Well, how do you continue? Do you know how to overwrite this thing here? This is a determinant, so you can use the laws that determinants have. For instance, if you have a 3 by 3 determinant, you can use this method of going through the first row, and then you cancel here, you have x times b, c, b, w, minus, etc. So since this is a determinant, you can use the same trick. And the nice thing is, the small determinant is also a delta, the same thing. So you have this kind of identity. This is a way of dealing with this generalized Kronecker delta. Since it is a determinant, you can go by the first row. That's why you always have alpha here, because it's the first row, and go column by column. So the first column is mu, then rho, then sigma. And the signs are alternating, plus, minus, plus, minus. And here, you have the same indices, but without the one that went away. So in the first one, you have mu, here you have mu, and these ones continue in the same order. You just pick one out. So I'm going to give you a homework to use this identity here. Actually, you have to use it twice. You use it once like this, and then each one of these you break again. And then you can show the following. Use the notation we have much better. So this is the Ricci scalar squared. This is the Ricci tensor contracted with itself, and this is the Riemann tensor. And I have a terrible mistake here. I'm going to correct it right now. It's minus 4 times 6. It has to be 4. This is a very peculiar combination of character square terms. So if you recall from the talk we just heard, we had sometimes this term, we had sometimes this term. This term never appeared. And there's a reason for that. And the reason is this combination, this very particular combination has a name. This is the Gauss-Bonnet density. And the thing is, in 4 dimensions, the integral of this is a topological invariant. Which means it's completely, or almost completely useless as a Lagrangian. Because you change the shape of the manifold, and this thing doesn't change. The only way to change the value of this integral is to really change the manifold to make a hole through it. And this then will change. And it's, if you normalize it properly, this is actually quantized. And it counts how many holes the manifold has. So it has one value for a sphere, and it has the same value for a cube, for instance, but it has a different value for a torus, which has a hole. And if it has 2 holes, then it has another one. So this means why do I say almost? Because you may include it in the action because it doesn't hurt. And if you include it, and if you try to quantize the theory, then the action integral can tell the difference. Because if you change the topology, this will change. So in the action integral, this will assign different values to different topologies. So that's a difference. So it doesn't change the classical field equations, but may assign different weights, different values to different topologies in the action integral. So this term and this term in the Lagrangian, you don't need this one. Because you can always introduce this and cancel the term that has this one. So you only need two. But of course, this particular combination has properties. And the properties are that since we built it from differential forms using only the exterior derivative, there are no higher order derivatives of the metric here. It's only second order derivatives. I can be a little bit more precise here, but hold on. Okay, so our L2 is what happens to L2 if we change the field line? For instance, if we want to compute the variation of L2 when we change the field line, what do we get? Nothing. Because it doesn't depend on the field line. It depends only on the spin connection through the curvature. So this is actually insensitive to changes in the field line. But we would like to compute its variation when the spin connection changes a bit. This is actually, it's useful to first compute the variation of the curvature with respect to this variation and then introduce this here. So recall when I was studying this for the first time, just a couple of years ago, I was a bit confused in how to perform this variation. For instance, if you write here a delta, and then you write here a delta, is there a sign change, for instance? Because when you compute the exterior derivative, there is a sign change. But what about the delta? Because the delta more or less satisfies Leibniz rule. But do we have sign change or not? The answer is no, we don't. But the reason why is that this is not a one form. The delta is just a variation. This is a one form, and this is a one form too. So the way to look at it is the following. We compute the Riemann curvature for another omega. We compute an R prime, which is the old R plus some correction. And only saving space here. So this is the new R computed from omega plus delta omega. And you just go through it. First thing here, d omega plus omega times omega will give you the old R. Here you have the derivative of delta omega. And here what do you get? You have omega times delta omega plus delta omega times omega. And the last term is delta omega times delta omega. That's too small. Quadratic. So you see, delta R is just so in simple terms, there is no sign change. But we can do a little better than that. We're going to mess around with this term here. So this is a one form, this is a one form. I'm going to interchange them. So I get minus okay. Now I'm going to be very evil. I'm going to change the order of the indices here. So instead of CD, I have BC. And this gives me another sign change. And then I'm going to change the position of the C's here. So I'm going to put this C down and this C up. And I get a plus. So I have the derivative of delta omega plus two terms. The first one is the connection acting on the first index, and the second is the connection acting on the second index. That's the covariant derivative. That's a nice equation. So actually the variation of the Riemann curvature, of the two-form curvature, it's the covariant exterior derivative of the variation of the spin connection. That's what it says. Okay, so was this clear? Is it okay? So now I'm going to use that here. So when I multiply, what do I get? I get first L2. That's what I get. Again, the last term, it's quadratic, we forget about it. Now this is a two form. This is a two form, so I'm going to interchange them. I get RCD beta RAB. And I'm going to move around the indices of the epsilon. Instead of ABCD, I will have CDAB, which if you check, it's an even type of interchanges, so I get a plus sign. In the end, this term here is equal to this term here. So what we get is the delta L2 is 2 times and now I use that. And here's the nice thing. This R has zero covariant derivative. It's one of the Bianchi identities. So I can take this derivative and write it here at the beginning, acting on everything. Because of the identity, because the derivative of this guy is 0. And this is a covariant derivative acting on something that's a scalar that doesn't have free indices. So this is actually an exterior field. And this is the proof that this Lagrangian doesn't give any field equations, because its variation is a total derivative. So this is because L2 is a topological invariant. So we perform the variation, and here we get 0, and here we get a total derivative. And if you integrate, you can say, okay, we'll choose the variation to vanish in the boundary of space-time, so we get nothing. So in 4 dimensions, this L2 doesn't do anything. It doesn't change the field equations. So of all the Lambda terms, we have the cosmological constant, the Einstein-Hilbert term, and the Gauss-Bonnet term doesn't change the field equations. So it's very harmless. So we get the old theory with almost no change. Actually, this term is also important for a different thing. This is a bit more technical point, but if you are computing the conserved charges, the nether charges, then the boundary terms are important. They will change the value of the charges. And people have shown that if you want to have well-defined charges, like the mass, the charge, whatever, then you need to add the story. So it doesn't change it in the page, but it contributes here. So I did this with all detail. I'm going to give you the rest as homework. So that's what the other two terms do. L1 will give you the Einstein field equation, this part, and L0 will give you the cosmological constant. And the field equations, we have two sets of field equations. One when we vary with respect to the field line, and another set when we vary with respect to the spin connection. And when you complete the second set, you have that the torsion must be zero. And this is a field equation. It's not something that I'm imposing at the beginning, a priori. It's something you get at the end. Of course, when there is no matter present. The torsion equal to zero you get as a field equation in this context. Okay, any questions so far? So now let's free our minds and remove d equals 4 and see what happens if we go higher or lower. So we have the same ingredients. Plus the Minkowski metric and the epsilon tensor, which has d indices. And you can play the same game that we played last class and start multiplying these things together to build up d forms which are Lorentz invariant. And if you want to check if you have played the game nicely, then you have to go to the following paper. So what Bardones and Sanelli did was they systematically search for all the combinations, all the possibilities of multiplying these things together and find Lorentz invariant deforms that are candidates for Lagrangians. And there are many possibilities, but not infinitely many. So you can classify them. And well, there are many things, but the Lambda family is still there.
But did they put any sort of condition to avoid higher derivatives, or they are just putting all possibilities together?
The nice thing about this formalism is that higher derivatives are absent automatically.
Anyhow, I see.
Because because of this. But they are not using the Hodge duals. The Hodge dual is a way to map a P form into a D minus P form in D dimensions. It's a duality relation. But the thing about this is that it uses the metric. And the metric inverse, actually. And so it's not fair play here. Because for us, the metric is a derived thing. These are the ingredients. Using the metric explicitly, it kind of does some breaking the rules a little bit. Okay? So if you don't use the Hodge dual, you never get higher derivatives. And so it's automatic. So this is the most general Lambda Lagrangian. It's a linear combination of different terms. The LPs are the same LPs that I defined recently. So you have L0, which is all field lines. L1 has one curvature, and you fill the rest with field lines. L2 has two curvatures, and so on. And so here, this LP has P curvatures. And here you have So this is a 2 form. Each one of these is a 2 form. So this is a 2p form plus b minus 2p, because each one of these is a 1 form. And so the result is, so this is a d form, which it must be. So this is the general Lambda Lagrange.
Sorry, why doesn't the T, why doesn't the T, and why isn't the T considered then? The torsion.
Well,
just put the curvatures.
it's just because we are considering this particular family of Lagranges.
I see.
Actually, you cannot use the torsion in a construction like this, because if you put 2 torsions here and you contract with the epsilon, it gives 0.
I see.
But you can use different things. It's not impossible to use the torsion.
Yeah.
There are, in this paper, there are many possible Lagranges that include torsion.
Okay, I see. So this is not unique.
No, this is not
I
unique.
see.
This is a family within all the ones that are considered.
Okay, I understand.
But if you put the torsion, or if you don't want the torsion to appear,
I see.
then this is more or less the only choice.
Okay.
All the other Lagranges are related to torsion, even when they do not have the torsion explicitly there.
I see. I see.
L2 is a topological invariant in 4 dimensions, but not in 5. So if you are in 5 dimensions, for instance, the L2 is 2 curvatures and 1 field band, and this is the same L2 from 4 dimensions. If you turn into tensor language, it is still the same thing, but it's no longer a topological invariant. So this does contribute to different field equations, to different physics in 5 dimensions. But for instance, L3 is a topological invariant in D equals 6. That's a topological invariant. But not in D equals 7, for instance. So what you get here is a series of dimensionally continued topological invariants. For instance, this is a topological invariant in 2 dimensions. This is a topological invariant in 4 dimensions. Etc. But if you now take this same guy, but instead of looking at it in 2 dimensions, look at it in higher dimensions, then this gives you a lambda diagram. And so in even dimensions, you always have the option of including the last term or not, because it's a double eigenvalue. But this doesn't happen in odd dimensions, because in odd dimensions, there's always one field line here at the end. But in even dimensions, you can fill this with only curvatures and no field lines. And that's a double eigenvalue. And the tensor equivalence of these topological invariants are incredibly complicated. I show you the Gauss-Bonnet term, which is quadratic. This is relatively simple. But if you look for the third order term, it's a messy combination of Riemann tensors contracted among themselves of all the possible ways with fixed factors, with fixed numbers in front of them. And only with these fixed numbers, this is a topological invariant. It is not invariant if you change one number. So it's very nice to write it this way because this is very simple. Okay, so this breaks a taboo which says that if you have higher powers of the curvature, that means that you will have higher order equations for the metric. That's not true in general. I mean, it's true in general, but it's not true for these cases. These are the exceptions to the rule. So if you have r squared minus 4r mu plus this thing here, and you take this and you integrate in 5 dimensions, this will give you a Lagrangian and field equations that do not have higher order derivatives for the metric, but only for this combination, only for 1 minus 4, 1. Any other combination will give you higher order equations. So this is why people look at these theories, because they have this special property.
Eduardo, what you say is that these terms are topological invariant terms in these spatial dimensions. Now, this same Gauss-Bonnet term in 4 dimensions, it's a topological term. But if you go to 5, as you did, you say it is not, but it anyhow does not have higher derivatives. Higher derivatives are always excluded by them, by this spatial combination.
In all the lambda terms.
I see. Okay.
So it's in 4 dimensions, it's a topological invariant. In 5 dimensions, it's not a topological invariant, but it's special.
Yeah.
It's not anything. Well, but there are some drawbacks, of course. And one thing that's not very nice here is this. That in principle, you can multiply every lambda term by an arbitrary constant. There's no way to, a priori, there's no way to fix these constants. Because this can be anything, and this will still be invariant under Lorentz transformation. So for instance, I haven't really spoke about this, but the field bind is not dimensionless. It has dimensions of length. The Riemann curvature is dimensionless. So every term here has a different dimension because it has a different number of field bind. So the constants are not dimensionless, they are dimension full. And people don't like this very much because, well, we heard it in the last talk. It gives arbitrariness to the system, and since the constants are dimensionful, it diminishes the chances of the theory being renormalizable. So this is considered to be a problem. In D equals 11, we have n equals 5 because we can put 5 curvatures here and 1 field bind. And these constants are really important. They are not just for fun. And I'm going to tell you a little bit about a work I did in which it's very clearly shown how this happens. So So in 5 dimensions, we have cosmological constant, Einstein-Hilbert, and the Gauss-Coulomb term, which is not a topological invariant in 5 dimensions. And so there are 3 constants. Of course, you can always choose one and do it like this. And so this becomes a global constant that's not very important. And so you only have 2. And this one is related to the cosmological constant lambda. And from this one, we build up a constant alpha that actually it goes multiplying here. And the behavior of the theory depends very strongly on the value of these 2 constants. For instance,
Eduardo, is it true that this way you lose track of the gravitational constant? Or you can, because I mean, for us, we always associate the gravitational constant to the Einstein-Hilbert term. Now you factor this term out, this constant out, and you have the ratios, and one ratio is lambda, the other ratio is this alpha. So if you want to reconnect with the Einstein, with the gravitational constant, how should we proceed?
This alpha 1 is related to the gravitational constant.
Yes. But since it's a global constant, I am throwing it away, let's say.
Yeah. But it's the same thing you do in Einstein-Hilbert, because you have 1/16 pi j
I see.
times, I'm going to write it in pi.
Okay.
It's r minus 2 lambda,
Yeah.
and here it's plus alpha times the Gauss momentum.
Yeah.
So the Newton constant is there,
Here.
but the behavior of the theory depends on these constants
With the relation of these two.
so the relation is this.
I see. Okay, it's clear to me. Thank you.
So I'm going to continue.
Sorry, Eduardo.
Yes.
The last fraction, isn't it? Alpha 2 under alpha 1
Yes.
instead of 0.
I got it completely wrong. Thank you. That's it. That's it, yes. Thank you. So the simplest solution of this theory is a spacetime that has constant curvature. Such a spacetime has a very simple Riemann tensor. And of course, sorry. Thanks. This is a very simple spacetime because all the components of the Riemann tensor are given in terms of one constant. So this is called a constant curvature spacetime. And you can take these ansatz and plug it in the field equations. But the field equations are quadratic in R. So you get a quadratic equation for K. And this quadratic equation, of course, has two solutions. Or maybe one. Or maybe zero. It depends. So you have a picture like this. So here in between, you have two solutions. There are two values of K which solve the field equations. Here, you don't have any. And here, along this curve, which is a hyperbola, you have one. The hyperbola is actually, so if alpha times lambda is equal to minus 3/4, then you have one solution. But if alpha times lambda is greater than this value, then you have two. And if alpha times lambda is lower than this value, then you have none. So it's like having different theories actually. So the theory is very sensitive to the value of these constants. For instance, here you don't have a constant curvature space-time, so the ground state has to be something else. So what I was actually looking for was, what is that something else? But my point here is that the constants really are important. They really shape the theory. They give you very different behavior depending on these combinations, these kind of things. So, is it clear? There are any questions?
Is there any sort of condition which restricts the sign of alpha? That I say positivity or alpha can be positive or negative?
In this context, there is an end.
No condition.
But the same Lagrangian you can derive from string theory arguments.
Yeah.
And the string theorists say alpha must be positive.
Yeah, that's what I was guessing. I see.
But here you really don't see any reason why alpha should be positive.
Why, if you derive from string theory, alpha must be positive?
I really don't know. I saw it read.
So there isn't a fundamental argument.
There is some, I guess alpha is related with something like that. Because this is actually the dimension of alpha. The cosmological constant has dimensions of 1 over length squared. And the alpha has dimensions of length squared. So the product is dimensionless. And I think it is because of this. It's the square of some length. So it has to be positive. But the detailed argument, I don't know. But of course, that's the thing you want to do. You want, if the coefficients are so important that they determine the behavior of the theory so much, there is one question that comes to mind, and it's the following. Or at least restricted in some way. And the answer, of course, it is. And I'm going to give you a reference here of one way of doing it that I'm not going to follow. So that's why I'm going to give you the reference.
Just a curiosity, okay, in this paper they fix the coefficients. What are the dimensionally continued black holes?
Well, it's dimensionally continued because they're using the lambda Lagrangian. So it's like taking this topological invariance and do the dimensional confirmation. That's its sense. And what they do here is actually they look at pictures like this and they say, okay, we're going to demand that there's only one solution for this. We don't want 2, 0, or many more. Because if you have, this is the quadratic equation, that if you have 5 powers of the curvature, you can have many different solutions. And here they demand we want only one. And this fixes the coefficients in terms of just 2. So instead of having n plus 1, you have 2. That's what they do. And they call it the dimensionally continuous, of course, because only 2 years before this, they were discovering the 3-dimensional black hole that is the most cited paper in Chilean physics. And, well, this is the generalization to higher dimensions.
Eduardo, are you going to show to us the connection between these terms which